So in the last video, I talked about how typically one uses Green's theorem to convert a nasty line integral into a less recalcitrant double integral. This is an example of one way or one instance in which it's beneficial to go the opposite direction. So if you want to compute the area of a funky shape, and the way it works is totally crazy. It kind of gives you some respect for Green's theorem. So we're just going to choose any vector field so that it has components p and q such that dq dx minus dp dy is equal to 1. So there's a lot of degrees of freedom in this. There's all kinds of things you could do. Okay, so then if you want to find the area of some region, then typically you could set this up as a double integral over d of 1 with respect to area, right? But since we've cooked up some vector field to be nice, we can rewrite this as dq dx minus dp dy, and then we can use Green's theorem to convert this into a line integral, and it's going to be the closed integral around c of p dx plus q dy. And so then it's just a question of like, okay, so what p and q do you want to use? Well, like I said, there's loads of possibilities. So some common ones, for example, are we could take f to be 0x. We could take f to be minus y0. We could take f to be minus y over 2x over 2. There's all, different kinds of things that you could do, right? And each one of these choices gives you an area formula. So then the area of D is going to be, and you can check, by the way, that each of these f's has a curl of 1. So let's see. So for the first one, that would result in this integral right here. For the second one, that would result in minus the integral c y dx. And for the last one, this would result in the integral 1/2 the integral of x dy minus y dx. And in a given instance, one of these might be easier than the others. So, for example, suppose you want to find the area of an ellipse. So x squared over a squared plus y squared over b squared equals 1. Okay, well, we can parameterize this puppy with, let's see, a times cosine t, b times sine t. So multiplying the first coordinate by a will stretch it horizontally by a, and then multiplying it vertically by b will stretch it vertically by b. Okay, and it's the usual t goes from 0 to 2 pi. So then let's see, if we want to find the area of this ellipse, if I used the first version from the above, then this one looks like 0 to 2 pi a cosine t, and then times the derivative, so that would be of derivative of y would be b cosine t dt. And so then I'm going to get ab times some integral that requires a trig identity, and maybe I don't remember the trig identity, or I'm afraid of cosine squared or something. I can solve this one a different way. I can do it instead using the third option. So 1/2 closed integral over c of x dy minus y dx, which in this instance will give me 1/2. Let's see, so we're going from 0 to 2 pi. So I'm messed up there. And so then we get AB cosine squared t plus AB sine squared t dt, which is easier. So this is just A over B, sorry, AB over 2 rather, times the integral of 1 with respect to dt. And so that just gives me pi times a b. So that's cute. You can see that if a and b are equal, in the case of a circle, that's where you get the a squared from. So this is kind of like the round version of a rectangle as opposed to the round version of a square. All right, well, now things are getting stupid. But anyways, so as you can see, there's lots of things that can be done with this. One thing that's really actually crazy is that it is possible to build a physical instantiation of Green's theorem, and it's called a planimeter, and these used to exist. Actually, my dad, when he was a silviculturalist for the forest industry, he used to use one of these with satellite photographs to estimate the areas of certain regions. And the way it goes is you have some device, and it's got like a little reader arm here, and so as you you track around the object going back and forth, and this thing is moving up and down, and this thing is moving side to side. Actually, the modern ones are polar, and they have like a beam arm that goes like this, and it can rotate like that, but never mind. What happens though is as you go around the boundary right here, this little wheel, it only rolls, it's on a rigid fixed axis, so that it is rolling in this direction. It doesn't spin like a sphere, it's just a little cylinder here. So in other words, when you move it across the top part here, it just skids, barely rotating at all. When you move it vertically right here, it rotates a lot, rotates a lot, rotates a lot, rotates a lot. But down here, it just skids as you drag it along. And the gears keep track of how much that little wheel is rotating. And so the little clock turns, the gear turns as you drag this thing around, and it gives you a running readout of how far you've gone, and it'll tell you what the area is by the time you're back to where you started from. It's fascinating. So there's this thing, I mean, you shouldn't be able to figure out how much area is in a region just by walking around the outside, right? But this thing is called a planimeter. You can even find them on eBay. And there's a section in the book that talks briefly about them as well.